where you have recording in progress, where you have the 1720 line preferentially seen in emission most of the time, even in the diffuse stuff, whereas the 1612 line is seen preferentially in absorption. I should stress that we don't strictly know in this data set whether we're seeing an inversion because we're looking at brightness temperature. We don't have a measure of the optical depth or the excitation temperature, but the fact that you're seeing emission against quite a bright galactic background suggests that it is likely to be inverted. Yeah, so let's see, survey specs is low resolution. It's 15 arc minutes, so it's pretty blobby looking, but it is pretty sensitive. And the data is released. I'll share the link again later. Yeah, and any mazes that you see here were followed up with the compact array in a series of papers by Hati Kao. And Chika Ogbodo, who's been here in this meeting as well, also published a subset of mazes that you'll see in this field because we didn't follow up ones that were already observed in MAGMO, and the remainder of the MAGMO catalogue will also be coming out. So all the mazes you're seeing here will have interferometric follow-up observations published, either have been or will be done so shortly. So obviously just talking about a survey is boring, so I wanted to talk about some of the science that we aimed to do with this survey. So when we conceived of SPLASH originally, one of the major motivators was looking for CO dark gas, H2, throughout the galactic plane. I don't need to motivate that more, I think, to the audience here, I hope. In reality, things turned out to be a lot more difficult than we expected in that regard, and I'll tell you why. So what you can see here, there's quite a lot going on in these panels, but on the top row, you have 12 CO for 3 different velocity channels. So the columns you can see are velocity channels and the rows are different transitions. So 12 CO is sitting at the top, and then the 4 OH lines are sitting in the bottom sets of panels. Sorry, I changed my color scale because it was from a different paper. So dark blue is absorption and red is emission in this. Red and green and yellow are emission. Without going into too much detail, you should be able to just eyeball this and see that you can see a lot more 12CO extended over the field than you can OH. So we unfortunately made the unexpected discovery of OH dark CO in this survey, which was a little bit sad for everybody concerned. But when you find something like this and you don't expect it, you've got to figure out why. Yeah, so we saw no spatially extended CO dark layers in contrast to outer galaxy, in contrast to local clouds, and we had done the sensitivity calculations, at least we thought we had. We thought we'd be getting something. So what was going on here? Oh, I just put this in case you prefer an LV diagram. If you're more of an LV diagram kind of person, this is a slice then through, where are we at? B equals 0 to B equals 0.45 degrees, integrated in latitude. You've got a longitude velocity plot. Different colors again, I'm sorry, you're back to red in emission and blue in absorption. The outer contour is 12 CO detection, and all the color you're seeing is the OH. This is actually quite a nice map as well, just to show you what a nice job the satellite line 1720 does, a sort of tracing spiral arm structure, maybe in contrast to the main lines, which can get a bit more confused. So the point to make here is that all the OH is basically inside the contours with a very, few exceptions. And the exception you can see near the galactic center is baseline problems. So when you can see that bit kind of streaking out around L equals 0, that's a lie. So fundamentally, it's the same thing, just being shown in an LV plot. Right, so what was going on? So let's zoom in on one of those channels. This is a 12 CO on the bottom and 1667 on the top, showing that unfortunate characteristic where you're not seeing extended OH envelopes. This is the continuum, the 18 centimeter continuum contours in this part of the galaxy. The survey also has continuum images available overlaid on that map. So, and I've highlighted the 10K contour there. So you'll recall your basic radiative transfer, and you'll recall the fact that your brightness temperature is determined both by the optical depth and by the difference between the continuum background and the excitation temperature of your OH line. So what we think the problem is here is that as you get off the dense midplane and as you start to get up to the plate, the latitude where you might expect to see some kind of puffed out, thicker disk in CO dark H2, as Michael Bush has, shown in his work, that's the point at which your excitation temperature starts to get rather close to your continuum. So just to have a look at this histogram from D. Lee and others' work on OH measuring excitation temperatures directly, The excitation temperature of the main lines ranges from like a couple of Kelvin through to maybe 10 Kelvin. So that TEX minus TC term actually gets pretty small around the place where you were probably hoping to try and pick up some of those detections. There's some caveats here, of course. You don't know where the continuum is along your line of sight, and I'll get to that in a minute. But overall, you can quantify this a little bit, and we did so in the pilot paper of this. This plot simply shows if you take a kind of characteristic diffuse OH column, even quite a high diffuse OH column, and you plot the excitation temperature against the continuum background temperature and ask whether we could detect that material in splash, the answer is a big chunk of it we can't detect. So there's a decent chance that there may be stuff here, but we're just not, unfortunately, the continuum background is such that we really don't have a good contrast. So the sensitivity we thought we would be getting, we hadn't really thought that through, it turns out. So, oh yeah, I put a little caveat. Anomalous excitation in the satellite lines can help you a little bit. There's times when you pick out something in the satellites that you don't see in the mains, but the basic point still stands. Okay, so we thought an alternative approach. There's still much, we haven't gone further with this at this point, but there's still a lot you could do. So you could forget about looking off plane at where you think things will start to get diffuse at higher latitudes. And you can stick to the midplane where your contrast is high because of all those H2 regions and bright synchrotron emission there. And you could focus on comparing your column densities. So you can pick up your OH column densities and your CO column densities and go component by component and try and figure things out. But when you try and do that, the ordering of things along your sight line matters a lot. So you can have a cartoon, you can imagine a cartoon like this. Our survey area is sitting in the triangle on there. The pink is on what I'm imagining some kind of diffuse synchrotron component looks like. There's a bunch of H2 regions I've dropped into the plane. And along any sight line, you've got some unknown ordering of H2 regions, synchrotron and OH clouds. So you've got a complicated radiative transfer equation. And you need to know the answer to this. Like, it really matters. If you get this wrong, it really goes very wrong in terms of the column densities that you derive. So you would need to incorporate our knowledge somehow of all the other traces we know in position, velocity, which includes H1, H2 regions, recom lines, CO, 3D dust, and all this junk. And my dream is that me or someone is smart enough to make a big fancy Bayesian model that determines the most likely solutions based on a bunch of intelligent priors that we have. But it would definitely not be easy, and it's not something that I myself know how to go about. Like, people are starting to do things like this, but whether it's, whether the payoff is worth the pain, I don't know. And in the original version of these slides that I cannibalized, I'd had a little footnote that said, ask me about just how wrong it can go and look at my paper for a terrifying plot. And then I thought, I'm among friends here, I'll show you the terrifying plot. So this is the terrifying plot. It takes a bit of explaining. I will summarize very briefly. You have the fraction of the back of the continuum that you see along a sight line that is behind the OH. That's what I've parameterized on the bottom. And then on the y-axis, you have the beam filling factor of the OH. And this is a plot I generated for a typical set of observed conditions. So I assumed an excitation temperature. I took some typical observed brightness temperature, something like that. And I asked how different the column density, the beam averaged column density, NOH star, could be based on what fraction of the continuum on my sight line was really behind the gas I was looking at, and how my beam filling factor was in OH. I think that was a beam filling factor. Anyway, you can look at the paper. But the point to look at here is that you have something like 2.5 orders of magnitude wiggle room in your derived column density, which is not a comfortable position to be in, just depending on what assumptions you make about how things are organized along a sight line and how filled your beam is with OH and how filled your beam is with continuum. Like, it's not a good problem to be, it's not a good situation to be in. So if this is to be approached properly, it has to be done very carefully. But one door closes and another door opens, and Anita has talked to you about satellite line flips a lot already a couple of days ago, and this is one of, indeed, us sort of seeing a lot of these flips in Splash was what really triggered some of that work. So when I came to put the data paper together as well, I did a bit of a kind of quick and simple extraction of flips, and there are many of them, and here are some of these beautiful examples. And I won't go into the details about that too much, because Anita's already gone into it and Beth's talked about it too, but we indeed suspect that flips may be telling us something about where H2 regions are interacting with the surrounding gas, and that's interesting. And again, the data is available. And if anyone feels like diving in and trying to extract flips out of Splash in an intelligent way, rather than me, which was like picking out a few sightlines with my eyes, then the data is there for you, and it would be amazing if someone was keen to do that. So more fun stuff on the satellite inversion. If you care about such things, you can go through the cube and look at the statistics of where you're seeing different senses of the satellite lines in emission or absorption. So let's have a look here. So what I've plotted here, I've done something a bit simple, and I've looked at just voxels, so position velocity pixels within my 3D cube. I haven't fitted components. I haven't extracted clouds or lines. I've just looked at pixels. And I've looked at which one, I've picked out a pixel and asked which sense, like I've just plotted the brightness temperature of the two satellites in a given voxel. And so the second quadrant up there is when 1720 is inverted, and I put that in quote marks because we cannot confirm for sure that it's a true inversion, but it is an emission against bright background. Down here is where 1612 is inverted, and you can already see just from the number of pixels there that the 1720 is the predominant sense of the inversion when you see it. Now, here, this massively filled quadrant is no inversion, and I'll talk about what that is in a minute. I've color-coded this left-hand plot according to some proxy for line width. And again, I didn't fit components, so I had to do it a different way, but it's telling you roughly how contiguous that feature is in velocity. And you'll see that the ones with no inversion, A, there's loads of them, and B, the line width is huge. And what you're seeing in that quadrant is stuff like this, which is the central molecular zone, which doesn't dominate things spatially, but does dominate the number of voxels I detect because these ridiculously broad, very disturbed molecular absorption lines are sitting there around the galactic center. So in the central molecular zone, it turns out that the satellite line inversion that we see everywhere else really commonly in the galaxy is disabled. And it appears that that's just to do with line overlap considerations, because of the way that the ground state lines get pumped. If you spread things out in velocity such that some of those downwards pathways that used to be distinct end up overlapping in frequency, you wash out the inversion altogether. And it seems that that's what's happening in the CMZ, which is maybe not a surprising result, I found out, having looked into the literature on how these inversions work, but I thought it was rather neat, so I thought I'd mention it here. So that was all I was going to summarize on Splash, apart from to say, go to this link. The data cubes are there. They're just sitting there as standard FITS cubes. They're not very big. We also have calibrated single dish continuum for every one of these transitions, and everything's publicly available. And I think there is a lot of untapped science in this data set, and it's really a people power problem. So the survey team, such as it was, is sort of largely retired or disbanded or moved on to other things, but the data's done. So if anybody wants it, please go get it. If anybody wants to work on it, please work on it. If anybody wants to tell me about what they're doing, please do. I probably know what's going on in these cubes better than most people and can help you with pitfalls and weirdnesses and anything like that. But yeah, it's there for everybody, so knock yourselves out. Now, part 2, now a future survey, hopefully coming soon in the future, GASCAP OH. So that's the Galactic ASCAP Survey of OH. So we've got a nested acronym there. So ASCAP stands for the Australia Square Kilometre Array Pathfinder. I'm not sure how much this particular audience knows about ASCAP, so I'll give you a very quick summary. So ASCAP's an SKA Pathfinder built in Western Australia. We've got 36 12-metre antennas, baselines from 22 metres to 6 kilometre. The really novel things about ASCAP are a couple of things. One is its phased array feeds. So we're not doing single pixel detections anymore. A single footprint on the sky from ASCAP is nearly 5 by 5 degrees. So it is a very powerful survey instrument. And the other thing that's amazing about ASCAP, it's in an incredibly radio quiet zone. So the population density in the area of the telescope is something like 1 person per 500 kilometers squared. So in terms of human activity around the telescope, it's pretty radio quiet. We still have issues with satellites and other things like that. But overall, the site is amazing and the telescope is amazing. Yeah, and the basic band covers the OH lines, not simultaneously, I should point out, which is annoying, but we can get them. So what's GASCAP going to do? Here's our planned survey area. It covers a lot of the same area of Splash, but goes a bit wider. ASCAP is primarily a survey science instrument, and it runs for almost all of its time pre-approved survey science projects. So we're one of those projects. Again, we're getting all 4 ground state lines. In this case, we're not just Stokes I, we're going to get Stokes V as well for the mesas and the Zeeman splitting. Well, we're claiming that we're the deepest wide untargeted survey of ground state OH mesas and diffuse OH absorption. And we're going to cover the science areas you'd probably expect. So it's a star formation from the mesas, evolved stars from the mesas, it's molecular cloud evolution from the absorption, it's supernova remnants from the mesas, and galactic structure in the sense that you can pick out mesas for later VRBI follow-up. And I'll talk mostly, I'm going to skim over the science background, and I'll just focus on the top 3, which are sort of the major ones there. We do have a big survey team for this one, so I thought I'd take this opportunity to highlight who we are. So the PIs are myself here and Sherry Breen at the SKAO. We're in pink. Highlighted in blue are the team who have been slogging to try and get this up over the last few years. So there's Jay Kumar, who's here in blue on the right, Beth Capolazzo, who you heard from, and you heard from Jay the other day too. Beth's on the left. Shanoa Tremblay's moved on, but was instrumental in helping to set this up. And I've also highlighted in green above the other sort of very active members of our team in Japan. So there's Hiroshi Imai and Rina Kasai and Kei, whose photo I could not find. So Kei Hamada is not here, but those guys have also been interacting with test data and helping to get the survey set up. So what are the actual specs of this? You can take some time to look over the table later if you like, but we have essentially sort of 4 different surveys in one. We've got an LMC survey that's focusing just on the 1612 evolved star mesas. Similarly, a galactic bulge survey that's doing the same thing. Both of those will have multiple epochs of observations to try and capture some of that variability in the circumstellar mesas. Galactic Center, we plan to spend a lot of time there and try and catch variability in some of the star formation mesas, I believe. And then we're going to cover the galactic plane at one go per tile as well. And we can variously bin things up and change the resolutions around if we like to pull, we can bin up in velocity and improve our sensitivity for the absorption and leave it narrow for the mesas. So I'm not going to harp on about the science too much because I think that most of this audience is probably familiar with what we do with OH. But briefly, you're looking at your mainline mesas for late stage high mass star formation. You can imagine this, the classic cartoon of condensation of clumps through to star formation in a molecular cloud. And OH mesas tend to switch on towards the later parts of that evolutionary process. We hope to get statistics of thousands of star formation, about 1,000 star formation sites. This is going to facilitate model comparisons for physical environment stuff. Zeeman splitting, we very much hope will be possible. The Stokes V calibration at the moment is looking good. And it allows you to do your general statistical comparison with all of your different multi-wavelength surveys across high mass star forming regions. Evolved stars, now this is furthest from my knowledge base, so I always get a bit nervous talking to this star, and there's people in the audience, this slide, and there's people in the audience who know a lot more than I do. But your 1612 megahertz maser is going to probe mass loss from AGB and post-AGB stars and track the return of enriched matter to the ISM. So you can measure wind speeds and luminosity functions. You can hopefully uncover missing sources that have been missed in other surveys. And you want to understand wind driving and look at things like gas to dust ratios and mass loss rates. And you can do this with a statistical sample. And then onto the stuff I know better. What I'm really excited about doing personally is the potential for having hundreds of matched absorption sightlines in OH and H1. And the reason I'm so keen on that is because I'm interested in how you form the molecular gas out of the cold neutral medium. And the H1 absorption gives you direct physical measurements of the cold neutral medium. And the OH should hopefully give you direct physical measurements of the molecular gas. And you can be agnostic as to whether it's CO dark or CO bright. But with any luck, you can employ some of the excitation models we've heard so much about to try and constrain the physical conditions and match that statistically against what you see in the H1 and try and understand better how you set these starting conditions for molecule formation out of the atoms, and then whether the molecules retain any sort of knowledge of the properties of the atomic gas. So that's what I'm keen to do personally. And that's going to match up with our sister survey, GasCap H1, which will be mapping the plane in H1 absorption. So where are we at? So the current status, so ASCAP's been observing the sky for a while. But for a number of reasons, some of the surveys, particularly the spectral line surveys, have been very delayed. The observatory didn't even really get our modes going until quite late in the game. So we got our first test kind of data around 2020, but there are a lot of issues with it. So over the last 5 years, terrifyingly, we've had a series of sort of test cubes observed and a series of things, a series of improvements we've had to make. It's very slow. Like, I could talk for a long time about exactly why things are as slow as they have been, but to try and encapsulate it all in one go, it's been a mixture of the fact, well, a lot of it's to do with slowness at the observatory and the supercomputer end. It tends to take an extremely long time at the moment between observing something and getting to interact with it, and then getting to re-observe or reprocess and interact with it again, like a very long time. That's because, I wonder if I have that somewhere. I can tell you more about it later, but ask me offline. However, there is hope. We're finally feeling like we're starting to get moving now. So let me just give you some encouraging early results from test data we've taken. So this is a small chunk of one of our test fields. You can see on the left, the image is a continuum image in this case. We could do some improvements in the imaging, but it's not looking too bad. And in crosses are new OH masers, and in circles are known OH masers. So we've picked up a lot of new sources in our test field for this particular example. And we just showed a couple of spectra there. So yeah, 19 previously published and 26 new discoveries. So that does bode well for the discovery rate for people who want to gather many masers. In terms of absorption, there's a lot going on the left-hand plot, and it may not be worth explaining in great detail, but this is extracting a bunch of continuum sources, integrating over them, seeing if we've detected OH, and trying to get some relationships between the properties of the continuum source and our ability to detect the absorption. And roughly, it looks like we'll get up to about 4 detections per square degree, which is not bad at all. And some of the more extended regions we'll be able to map across. And then you've got a very preliminary spectrum from me on the right, but I think you should ignore that, because in my next slide, I will show you the work that Rina's been doing based in Kagoshima in Japan. So Rina has been looking at some of our test data. She's been figuring out the best way to extract bits of bright continuum based on the automated source finding that's in the pipelines. And she's been exploring, looking at 12CO, 13CO, and the 2 main lines of OH. She's finding some CO dark H2 in these absorption sightlines, which is always nice to see. So in the spectrum I'm showing in the middle, I would wave my hand, but I can't. The feature at -25-ish, weak in OH, definitely nothing in CO. And the feature at -40 something-ish, well, there's not a lot of CO there, like arguably some. And she's also been extending on the kind of work that Michael Rugel and collaborators have done with Thor, and follow-up surveys to that, and is looking at the relationships between the column densities in CO and OH, where both are detected. So that's part of Rina's master's project that she's currently working on. And so you can ask her more about how that's going. So data availability and team membership. So I should say first up that we are an open collaboration. So if you want to get involved, you contact me or Shari Breen, the other PI, or both of us, and we usually let people in. So a little bit more about how ASCAP works. So the ASCAP policy is that data products are public as soon as they're validated. Now, what does validated mean? Validated means that the team has looked at it and has decided that it is science, science good, whatever that means, is good for science. At the moment, we have not validated any cubes, and there's been a lot of reasons for that. In the ASCAP model, all of the data is calibrated and imaged in real time by the observatory using their pipeline on a supercomputer. And then the idea is that the beautiful science-ready data is served to us as the survey team. Now, and they don't retain the UV measurement sets. So that's a model that we need to adopt. I mean, the SKA is adopting that essentially too, just because of data volumes. It's not feasible to store it. In practice, it's been very difficult because every time we've needed to iterate on something, we haven't been able to do it ourselves personally, and the delays in processing have been really quite prohibitive, which is the reason that things have taken a long time to get to where they are. We can't tweak, we can't design our own things. Even tweaking our own cleaning parameters is a thing that takes months. So we still don't have a working pipeline currently, but we've made a lot of progress. Like we've solved many issues, and I should have put them all so I could check them off and show you, but we've solved a lot of issues that were troubling us earlier. Currently, we are verifying our flux density calibration scale is as we expect. We had some issues there to do with primary beam modeling and to do with how we spaced the path beams, the beams of the phased array feed. So we had to go back and re-observe and redo our strategy because the observatory's recommended parameters were not working for us. We're still trying to figure out the optimum cleaning approach because we need to retain the continuum. We need to clean that at least reasonably well in the galactic plane, and it's complicated. However, there's been a new sort of push recently at CSIRO, who manage the telescope, to really strongly work to get through these delays that all of the spectral line survey teams have been experiencing. And they are keen, very keen, to support us even by providing staff to us, observatory staff, to help us with our pipeline work so that we can have observations commencing fully by 2026, in which case we'd get done pretty quick. So it may be that we'll go from a long period of almost nothing to suddenly having an absolute glut of data. And that means if you have any interest in any capacity, please let us know. Join us, help speed this up. We could always use more people than poor Jay and Beth and Rena, who are really the ones who are stuck into the data trying to figure out what's wrong with things at the moment. So yeah, just let us know, and I will end there. So thank you.
Thank you for losing my voice progressively throughout the week. Thank you so much, Joe. That was so interesting. I noticed something that maybe it's a bit cheesy to mention, but I noticed that there's a lot of women working on GASCAP OH. That's really nice to see. Complete feminist side note. Good on us.
Yeah.
Yeah, it'd be so cool once we get this data going. But yeah, having worked in the same office as people who've been struggling with this data is, yeah.
I was trying to decide how much to go into it. Like it's been an experience.
Yeah.
It's really been an experience. Like, but I am genuinely hopeful. There was a time when I just didn't know if this was actually going to even happen. Like it felt intractable, which was pretty depressing. And now I feel hopeful, genuinely hopeful. So I do think we'll have data soon. And everything we're seeing now in the data is nice. Like Jay just verified our flux calibration finally, like a couple of weeks ago, after years of not understanding why things weren't matching up with simultaneous observations taken with the compact array. Like, but now I think we have an answer to that.
That's fantastic. Yeah, I know. I haven't been involved directly in this, but having been involved in commissioning of another instrument and listening to other people, like it's absolutely, it's not even invaluable. It's do or die essential to have knowledgeable astronomers involved in the process from a really early start. Because yeah, so many of the problem, like with crab path, there were some instances where they were going to bake in high flux thresholds to get rid of RFI, and I'm just like, masers, because you can't expect people to know everything. That's totally unreasonable. But yeah, we need to be involved in every step.
We had an issue that we had some data that we thought was going to be quite good that was taken years ago. And it turned out, obviously UV, remember the measurement sets have been deleted, right? So we can't go back and process it again. And it turned out that the Doppler correction was only being done once per 12 hours, which was, and that because it had been designed for extragalactic work and people hadn't actually just used, it was run by the observatory, something hadn't been switched on, so all the data ended up being useless because our masers were smeared out. And so that went in the bin. And then we had to re-observe it all again. So,
yeah. But yeah, you can't expect people who've never done it before to necessarily think of things so complex as the Earth's rotation.
No comment. Michael has a question.
That's me being mean. Michael.
Yeah, well, thanks a lot for the amazing talk. I just had a quick question for what you present on Splash. So this problem about the different gas parcels at different locations in the galaxy, is that a single dish problem, or do you think, or I don't know, is that for strong OH absorption observations, would you think that we don't really have the problem?
I'd say primarily a single dish problem, yeah. Sorry, was
Could
that the
we
end of the
learn
question?
something if we combine single dish and interferometry data? I don't know.
Yeah, we might
I was thinking
actually.
about TORGC, like which recovers some part of the data. And I'm currently finishing the reduction. So I was, yeah.
Yeah, so I think that's a really good idea, actually. I think the interferometric observations would help constrain it. So your issue partly with splash is that you're sensitive to all of the diffuse, like there's a big sort of whiffly diffuse synchrotron background that's completely resolved out in the interferometric observations. So that's one thing. Let me think this through. And I think part of it's the fact that the beam's so big. So you'd really be able to sort that out a lot more nicely with an interferometer. Yeah, I think it's mainly those two things. The fact that you can have OH absorption coming from almost anywhere along a sightline because of this synchrotron stuff. And you don't know where the bright concentrations are of continuum are relative to all of that. You can actually, I mean, like you say, you can sort of make some, it's not completely intractable even with what we have. You can make some sensible assumptions based on kinematic stuff, although it is the curve's dual valued in the inner galaxy. And you could make some sensible assumptions based on H2 region catalogs if you went through it. But yeah, an interferometer will be a lot easier. Won't have much of the same issue.
Okay, thank you.
Shinji has a question, I saw.
Oh yeah, yeah, I got a question. So with nice splash data or gas cup or X data, can you also make radio recombination line mapping, or it's out of band? No, it's complete.
No, it's the band's too narrow, and you haven't got correlator resources because of it's fairly inflexible.
Okay, yeah.
Michael, other Michael.
Yeah, well, first of all, thanks for the talk, Joe. It was really interesting. Thanks for the gas cap OH update as well. I'm very excited for Rena's project, seeing the CO dark OH. Yeah, that's right. I keep.
Yeah.
Sorry, it's not even that late. I'm already tired. Anyway, yeah, I just want to echo what you said about Splash. I think Splash is a great data set, and there's like loads to do with it. I wonder if, yeah, you had said about this aspirational statement about gathering all the observations that we have. Like we have OH, we have CO, we have H1. Now we even have 3D dust. Like there's must be a very smart way for a smart person to combine all of these.
Yeah, I know. I keep trying to get Trey interested. This is a Trey problem.
I know this is a so he had a wonderful talk for those who missed it on about Bayesian modeling and this Bayes spec code, and you can fit multiple lines together and put in priors, and this is definitely something that we need to sit down and do. So I don't really have a question. I just think like we're making progress towards that, and I'm really excited about that. So if anyone else is really excited about that, let us know and we can bug Trey some more.
I'd love to be able to do it. What worries me is that you'd end up sinking a load of time into it, and then scientifically, I'm not sure. I'm always very pessimistic, right? Like I'm always kind of seeing the problems in things rather than the potential, and that's a me problem. But I've been reluctant to sort of set a student on it because I think it would be really hard, and like I'm not sure like how much you'd get out of it on a sort of reasonable time scale. I still think it'd be awesome, but someone who dive into it who already knows what they're doing with this stuff.
And my even more aspirational goal would be to like get MolPop incorporated.
Oh my God, it would be so good.
It'd be really nice. Imagine. And I think that is really the final goal for the Bayes spec thing too, is just like do everything with radiative transfer from the get-go to predict all these complicated, flips and profiles you're seeing with splashes are really interesting and like seem like they have diagnostic usage. But we're just scratching our heads at the moment. And I think we're making progress slowly is what I want to say.
It's almost like it's almost like an AI problem, like the next generation of AI. You feel like just feed them all the bits and go off you go, like ChatGPT version 10. Like,
well, the problem with that is ChatGPT is very, very, very good at being very confident.
Yeah, I know.
And perhaps less good at being correct. But yeah, I did want to comment a bit on this idea of having like a big, Bayesian model that fits absolutely everything. I think what we need is, because you're right, of course, is it could potentially be a big, huge sink in time, and it could potentially not bear any fruit. But I think that the key that you would need for that would be to get a group of people who are brainy enough and knowledgeable enough, not only about the OH, but probably more importantly about the radiative transfer. And really think about, because, okay, so to say, like, in the most basic sense, what you need for a Bayesian model is you need a picture, like a bunch of parameters that describe the physical situation. So the ordering of the clouds, the velocity of the clouds, the column densities, you know, all of those kind of parameters that describe the situation, and have a way of then recreating what the observations would look like in the case of those parameters. And really the questions that you need to ask yourself is, where are the intractable degeneracies? And do they overwhelm things? Yeah, because if, for example, when you're doing optical depth observations, you can't disentangle optical depth and excitation temperature. They're like infinitely degenerate. However, if you can make some simplifying assumptions and say, okay, let's see what it would look like if the main lines had an excitation temperature of 5. Those kind of games. If you play those kind of games, then you can resolve some of these. So it's really about knowing what kind of, if there are degeneracies, what kind of assumptions are you going to be put in a position to make in order to resolve them? And does that ruin the science? You know, so it's those kind of questions as well. I would imagine just sitting here thinking about it for about 10 minutes. I think since the ordering of the clouds, like the closer the cloud, the more continuum behind it, you know, just that kind of a thing.
Yeah. You definitely could do things.
Yeah. I feel like it probably could be done. It probably could be done, but those are the kind of questions you have to ask beforehand. And I guess I'm saying that with the intention of that could be kind of sorted out with a week of smart people thinking instead of, you know, 6 months of somebody working on it. So yeah, it's just a thought.
Beth.
I was gonna ask, how much degeneracy do you expect from that? Like, you know, how the ordering, certain different orderings could end up looking the same result at the end. And like that would,
I'd have to think it through.
Yeah.
Yeah.
Because that would be the challenging part, right? Because if you've got many different ways things could be ordered, like, yes, you could constrain it based on if you've got H2 regions and then you've got distances to H2 regions, and that adds some constraints, and the dust maps. But
yeah, you could probably build a really simple model. You should pick some simple sightlines, and you could try kind of sketching a toy model probably without too much difficulty. I've just never really had the capacity and felt.
There's also a problem on the continuum, like you don't know where the continuum is
There's
changing.
relative covering factors as well, which is a horrible beast. I did. Sorry, no, you go.
No, I was like, as I said in the chat, the outer galaxy, the continuum temperature is relatively stable and nice. So, and there's no kinematic blending. So I wonder, but the thing is, we don't have splash in the northern hemisphere. So, maybe you do it for the couple spectra I have, which are not cubes. So I wonder how useful that is. I don't know.
It could be just, again, just thinking about it for like 10-15 minutes now. You'd be able to put a cap on the total continuum, at least, hopefully. And then it's like, what percentage of that is behind your little guy? I think that's going to be hopelessly degenerate with things like the excitation temperature of the line, because I imagine if you're increasing the continuum, you're gonna have to like decrease the, I don't know, there's gonna be some sort of interplay between those two. But of course, then that allows you to come in and potentially put limits on that. And if you put limits on what the excitation temperature of the main lines might be, that could then give you an idea of where the cloud is relative to the continuum, and could then allow you to look at, well, what is the excitation temperature of the satellite lines? I think there's ways around this, because if you're using a Bayesian framework, you can create, you know, priors of what the known distribution or the expected distribution of these excitation temperatures are, and they do tend to be kind of did somebody say Allison has a cat?
Yes.
Sorry, that was me.
Totally derail.
She
And
needs to
I
get a
think she
cat
has
back.
birds too. Allison is
Sorry,
I
Anita.
mean,
Yeah.
I don't know.
Sorry, John, who's waiting patiently to ask.
In your
Yeah.
talk, I could hear like chirping, and I was like,
Oh, it's a dog. I thought it was a cat.
It was the little frogs in Puerto Rico, but I think
It's the frogs. It's the frogs.
it's
Yeah.
the frogs. They're all the little frogs. Yeah,
Dog
yeah.
text.
I want to
Oh,
see a
geez.
frog. I want the frogs.
I want to go to John, but I wanted to say on your point, Anita, that in the cubes that Splash has, there are places, because the continuum varies, there are places where the line goes to 0 and then switches. So like there's places where you can say, oh, that's the excitation temperature, which is really nice. We can't do that in the outer galaxy yet.
And maybe that's enough to at least make a decent start, because again, that's the thing with these Bayesian models. Like if there's a key like anchor point that you can use, then you can you know, put that in your prior that says, okay, everywhere else not 100% sure, but right there I know what's going on.
Joe and I started, we took a glance at the regional Crutcher cloud and Splash. There's like a high latitude portion of Splash, and there's places I think we could do that with one of the main lines, but
It's not, like as soon as you get out the plane, it's not too hard, right? It's more about trying to get that whole depth through the disk. But sorry, John.
Okay, but
let's let John talk. He's been so patient. Sorry, John.
Hi, well, I wish I had a cat to show off to, or a dog. Let me say a couple things and then I'll ask a real question. First, you know, ASCAP was always going to be compute limited. And everybody knew that from the beginning, but nobody talked about it at all. And when by compute limited, I mean everything. That is CPU cycles and also data transfer and data storage and all of that. And it may be that we will come to a time when it's not compute limited anymore. But I think until we get to that, we can't really complain too much, although I certainly sympathize with everything you said, Joe. We've had all the same problems in
I know. People are trying to be very, I mean, no shade on anybody as an individual either. It's like everyone's doing the best they can. It's just been very long.
Now, going on to the problem of sort of the splash problem, if you like. And I like your words that you said we were looking for CO dark molecular gas in OH, well, that would be OH bright. But what we found was a lot of CO bright molecular gas that was OH dark. And yeah, but it's so dark. I mean, the point is, it's not that you don't see OH, you see it in deep absorption. And the whole question is, well, where is that absorption coming from? And more seriously, can we translate the absorption of the optical depth? Well, can we work out what the optical depth is? And then can we translate that into a column density? And that's sort of the problem that we're all thinking about. And let me say, I think that'll get a lot easier when GasCap H1 gives us the 21 centimeter absorption, because we'll have a lot. I mean, you have 4 sources per square degree, which is darn good, fantastic for OH. But, you know, we'll have probably at least 10 times that, if not, you know, 30 times that. And then that'll be the prior that we can put, because it's very unlikely that there'll be OH where there isn't H1 absorption. And so that'll help. But my question is this. So you've described a couple of wonderful surveys that are past and in progress. But with CryoPath, how hard would it be to go deeper with Splash? And, you know, you've discovered so many things serendipitously, like the line reversal in the satellite lines, that going maybe a factor of 2 even deeper might reveal really quite a bit more. So have you thought about what CryoPath could do?
Yeah, we have. And I should bring Michael and Anita into this a bit as well. But so yes, CryoPath could definitely do a deeper splash. We should maybe, but the issue at the moment is that it can't do, well, we're not sure what we do with the bandpass calibration. And we need to work that out first. It can't do frequency switching. And I guess since OH is everywhere, it's always going to be a bit of a challenge to do referenced observing. Same problem we found in Splash. Now, maybe it's tractable, but it's quite possible that the bandpass stability may be good enough that you don't need to. So Muradameh Saad is my master's student, who is probably, he was in the chat, he may still be here. I don't see his name on my screen, but he might be in the next screen. So Muradameh, as part of his master's, used UWL data, which was a different instrument, of course, but same telescope, looked at a high latitude cloud and observed OH deeply. and CH. And in the end, he found that we probably don't need to do referenced observing at all. It was good enough. We understood our calibration was great. There wasn't much bandpass wiggle. We could deal with what we had. But his lines are narrow. So as soon as you start going into the plane, especially where you've got like 100 kilometers a second of breadth, can we do that? I don't know. So we do have a proposal in led by Michael. We proposed to re-observe Radames cloud, didn't we, with the cryopath? Is that what we went for in the end? We did, didn't we?
I want to remind you that we're not allowed to talk about that, but
oh, we're
maybe.
not. I think we're allowed to say what we put in.
I thought it was dual anonymized, but maybe I'm wrong.
Oh well, everyone knows now. Nobody is anyone a TAC reader? I don't think anyone here is a TAC reader, are they? Sorry, well, Anita, you wouldn't.
I'm a voting member of the TAC, but no, it's fine because I'm supposed to say conflicts of interest, so that helps me to know that there's a conflict of interest.
Oh well, sorry, there's a conflict. It's us. Don't grade it, please.
No worries. I haven't started yet. It's all good. I think Jay's a reader as well.
But what would be a really good proposal is the one that Joe's about to describe.
Oh, well, but one that
Radame
you put in. Anyway, we're gonna look at the same cloud and we're gonna check what we can do. We've got very good calibrated data already. Baseline stability is going to be key. I don't know how we'll deal with it in the plane.
I wonder with the cryopath, because you'll have I wonder if it can be modeled in some super clever way. Because if you were doing because if you're doing a scan and you kind of know where the bright things are, maybe there's a way that we could be a bit more clever about that, because as you have point sources traveling through that field, known point sources, you know where they are, and look, because there's so many masers. maybe just the presence of all of the narrow features would allow you to reconstruct the baseline without the use of I don't know. It's getting out of my depth, like with like really careful calibration of continuum is not something that I actually do because I love the masers. Now I love the masers. I used to hate
I think I just want to look at how flat they are. Like, it's almost that simple, right? It's like, go and get on this guy, see what I can see, and see how stable they are and how flat they are. Like, they don't need to be flat if they're stable, but they need to be stable, really stable.
Stable across time, at least.
Because we're going really deep, like, and the lines are really faint, and they're also really wide. It was the same problem we had with Splash. The reason I released that data so late is because I spent way longer than I should have done fixing the damn baselines, like by hand almost at some points, which was not an experience I care to repeat.
Yeah, I feel like the expertise is down the hall from you. Maybe in the next meeting. But yeah, I would talk to them about what kind of bandpass shapes that they're getting. Ask, because a lot of the people there also worked on the UWL. Maybe they could give you some comparisons.
Well, the reason we're observing partly is because they came to me and said, we need someone to go and observe this to characterize the instrument. And then I went, let's observe this. So Max has his hand up there, and Max may know more about all this.
Well, I just felt that I probably need to comment on sort of ASCAP data reduction and, how it all comes into this and so on. Yeah, of course, I understand all the pain. I just feel that, well, all these issues with Doppler correction were raised even before any single line of code was written, just probably never got to the right level from us, or was ignored because priority was elsewhere. And honestly, like all things related to gas cap in general, not just gas cap OH, were essentially put on us without, they were just put into the requirements without any assessment of how complicated the system will become at the end, and whether it's all possible and how timelines will change. So of course it wouldn't be a surprise that we end up where we ended up. The current sort of issues, and you actually might know more about it than I do, despite being part of ASCAP project, that there is some sort of semi-artificial deadline looming about 2030. I don't know what it is connected with and why we push to do as much as we can before that formal deadline, and the fact that we actually, basically ASCAP is oversubscribed, but not in terms of the proposals, but in terms of the time available. And why time available is those 5 years rather than anything else. Maybe it's just the fact that the hardware life is estimated to be limited, and we don't have space, we don't have plan, and it's probably too expensive to replace it all. So yeah, I don't know. To me, you know, I'm happy to do a fair share of various projects, but I suspect there is a bit of a push to go towards EMU at least, and maybe Wallabies, and how GasCap will, well, in principle, you may be either told just accept whatever you have, but if you want to have more data or whatever. So it's an interesting question. I don't know how that politics will play up, but there is nothing technical in it. So that path to validate and, you know, see what problems are and so on, and like very slowly improve the parameters, we had to go through this. It is possible from my point of view. I'm not sure in terms of the resources and other things that it could have been sped up if, say, we had someone who is dedicated.
Yeah. Oh, he stopped. Oh, lost him.
No.
I know what he's going to say though. Oh.
Dedicated. We have some chats in the chat, I guess.
So those things are possible.
We missed you a bit, Max, because after you said someone is dedicated to it, you lost your connection for a while. But
okay, sorry. Yeah, I want to say that if we had someone dedicated who could look at the, say, single beam and process just like limited amount of data, but it should be enough to see problems. Like early on, it would have be helpful. Now I'm not so sure.
There's some discussion in the chat about Doppler correction. So Alison says Doppler correction could be done after the fact. No. So there's a couple of issues, as Anita mentioned. First of all, it was permanently smeared in some of our data and unrecoverable. What we are now doing is, there's another issue as well, because we've got a wide field, and the correction we need to make. So normally with an interferometer, you're going to set the correction in the UV domain looking at the phase center of the primary beam. So we've got a couple of issues. The first issue is that as you go towards the outside of the primary beam, the correction varies by a couple of channels. So you can't, any correction you apply in UV space is going to be increasingly incorrect towards the edge of that single beam image. In principle, you could then regrid in the image domain. We kind of can't, because our cubes are 2 terabytes each, and our final cubes, and so no one's going to do that. So the solution we came to in the end, and it gets even worse, because then a neighboring beam has a slightly different equivalent problem, and then a neighboring beam has a different equivalent problem, then you overlap them all and everything goes terribly wrong. So what we're doing now is doing a single frame. We're assuming a single frame at the center of the whole huge footprint that has 25 beams in it, which is going to get horribly bad towards the edge of the image. But we're also going to release a 2-dimensional correction image that anything that a user extracts from the cube can be corrected pretty simply with that computed correction. And if you had a supercomputer and plenty of resources, you could just regrid the cube. But it's not.
Yeah, apart from differential correction, which you cannot do, and all
and
this,
small,
fine things, and
sub-channel.
even whatever we have within the, well, I mean, even sub-channel, like, yes, while you accept that masers are point sources, you can pretty much correct every point, but what you have like between beams, so this kind of thing, if you only get the full image, which technically, like, some of us advocated against, because like if you get the catalog done sort of semi-internally for you, then it doesn't matter whether it's done from the original beams or from full mosaic. So you essentially lose information unnecessarily. And that normal Doppler correction algorithm, which goes from UV data to the cubes, in ASCAP soft, well, it was deliberately made simple. It could have been improved without too much loss on compute performance.
Jay's got his hand up, and
yeah.
Sorry, Jay was the one who worked on this for GasCap OH. Jay.
Yeah, thanks, Joe. No, I just I saw that comment on the chat, and I wanted to just said literally what you said about the Doppler correction, but just to clarifications on what Anita has said. The spectra is it was smearing out earlier on, but now spectra is not smearing out. Spectra looks absolutely incredibly matching as it is with the ETCA. So it's absolutely perfect. There's still early days for the flux, though we are very hopeful. but yeah. And the other thing, I think Joe might have intentionally missed, because we don't want to talk too much about gas cap OS for the moment. But I think the astrometry, as long as it's within the gas cap, it looks very reliable to within what we were trying to hope for at the start of the survey, or Joe could talk about that. But yeah, the velocity corrections was a big issue, and now it's I can say with fairly certainty amount the spectra that I have seen with simultaneous observations, both with ATCA and gas cap data, with multiple observations, it looks perfect match.
Yeah. So we're definitely good to sub 0.1 kilometers a second, less than 1/10 of a kilometer a second now. So after many, Jay deserves a round of applause for it, honestly. It's yeah, we got a working solution. It just took a while. And I would still in my heart of hearts, to regrid the entire cube and present it to the community kind of correct, particularly for absorption work. But I think we're stuck with what we're stuck with, unless somebody has a pet supercomputer they want to bring to the table.
Yeah, actually, I wanted to ask about that. Has anything been done about the intractability of the size of the data products? Because I remember when we were looking at pilot data, we couldn't find anything that could open it.
Carter will deal with it these days. And I think Max said something I wanted to address as well. I was just trying to loop back something about the politics of the situation. So we have been assured by CSIRO management, who has recently changed and are now extremely committed to sorting out the spectral line survey issues, really quite gratifyingly so. He said a dedicated person assigned to the survey would be good. That is planned. We will be assigned a dedicated staff member. The second thing Max said, what was it? Whether or not we get everything or just be happy with what we've got. The advantage of being a very small survey is we're going to get everything. There's almost no question about that now. I've been shown the predicted plots and they're pretty much you guys are tiny. You can just go anywhere. And I was like, can we have the promised time back that you didn't give us for a pilot? And they were like, oh, did we promise that? Yeah, probably. Because we're so small. There are 10,000 hour surveys on this thing and we are 500. So, and they're quite conscious that we've been a bit of the poor child not getting any of the food. So I think they're quite conscious that they could make that up to us fairly easily. So I am genuinely hopeful we'll get what we asked for. The issue is just, can we get a pipeline that works in time? Because it's just been really hard. Historically, the downtime between sort of requesting a reprocess, even of a single beam, and is getting the single beam to then look at is months, on the order of months. And that will change. I am really confident that will now change because there is motion within the organization to fix the issues that have been causing this. But
yeah, it's probably other things which people worked on rather than
exactly.
because the turnaround is reasonably quick now with the new machine. So it's yeah, if you if you want to reobserve and so on, you will have a week delay. But it's a question if everyone is asking nighttime and single wallaby track takes all the nighttime, then essentially
it's mainly
you can't
processing
get
and copying. It's processing and copying for us. It's just
yeah, it's in principle with old machine, yes, whatever we got was even less than we asked, even for wallaby, let alone other. And then yeah, basically people report bugs, and before you fix continuum, there is no hope you will fix spectral line.
I know.
So yeah,
I know it's not you.
I
know you guys are doing a good job, Max. Don't get me wrong. It's just from a consumer perspective, it's been frustrating. But everyone. I mean, actually, credit to the CSIRO people who've been active and helping as much as they had. Particularly Matt Whiting, who's not here, but has been an absolute god in just working with us and doing the things we need. But he's only one man, so it's me. Beth, hand up.
I wanted to comment on Anita's question about the data size. So yeah, like Joe said, the spectral line cubes are 2.5 terabytes. And as the final product from the survey, all we're going to get are these cubes. But there is a plan to, not quite sure exactly how it will work, but there will be an option to do cutouts of those cubes. So we'll do source finding on those cubes, and then if you've got a source of interest, you can get a smaller cutout around that because a lot of people don't need the full 2.5 terabyte cube for their science if they want to look at particular things. And we'll also do source finding on mazes as well. So that'll make it more manageable for the end user.
Yeah, I think we'll likely provide continuum cutouts around the continuum, like cutouts around bright continuum used for the absorption, plus cutouts around mazes. So they're going to integrate a cutout server into CASDA as well, into the data server. That's part of, there's something already in place, I think, but there's a project with the Australian, oh God, what's it called? SRC, what's it stand for? Science Regional Centre. The SKA Science Regional Centre. GasCap OH got approved for a project to get the computing support of the Science Regional Centre to do source finding, but also a cross-survey team group has got support to help do a cutout server as well. Sorry, Mad, my hand up.
So my question is, what's the future of Inspector for, analyzing and calibrating splash data?
Yeah, that's a good question. So Inspector is the name of the software package that's been developed for use with the Parkes ultra-wideband low receiver. So Splash is already processed. So in that sense, there's no need for Inspector, and Splash used a different data format prior to the current of SD-FITS. I've forgotten SDHDF that is developed for Parkes at the moment. So Inspector hasn't really got anything to add to Splash. Inspector would probably be used to process anything going forward, though. Anita, do you know if the cryopath's going to use Inspector?
Yes, it is. It is. Yeah. Who knows with how much success, but yes.
No, very successful, surely.
No, they I'm joking a bit. No, they actually changed the data format years ago in order to allow from the multiple beams of the cryopath. So no, I joke because I've got this long data set, right, that crosses all these changes. So I have so many ridiculous if statements in my pipeline. But yeah, it should. George sponsored me to ask that question.
George wrote the software. This is George Hobbs. It's Sarah.
I have a maybe controversial question.
Oh no.
I think you said you put a year on your last slide. Is that when we're going to get the data for GasCap OH?
Sorry, the story behind this is CSIRO, as Max said, has stuck a 2030 limit on the completion of the surveys for probably a number of reasons, some technical, some slightly political. So therefore they've built a timeline and they've been experimenting with how they can, it's a whole difficult logistics problem because you have to slot these different surveys in different places. Some of them have different daytime, nighttime requirements. The whole instrument currently takes hours to calibrate. Every time you want to change bands, it sits every one of its beams on a standard calibrator and spends time. So they're trying to fix that. But the point is, it's a very difficult kind of tessellation exercise. But they've got a number of different iterations of a schedule, and that has us starting in 2026. And I was like, do you think we can get our pipeline done by the beginning of 2026, CSIRO management? And they said, we will give you a person. And the person will spend a day a week and they will, champion your things, push your data through, like give you what you need when you need it. You can work with the people who do the cleaning. The clean model's been a whole thing. So we'll see. They do seem committed. This is a very different face than we've had from the organization over the last 5 years.
That's
it's just nice because there's been a real kind of an admission that things haven't been delivered rather than a sort of, people were always, I don't know, the management changed and the people who are currently managing have not been embedded within ASCAP land before. So I think it's a sort of fresh perspective on things.
Good enough for me, yep. Well, that's nice then that maybe it'll be observed in the future.
I know we are really now finally we're seeing spectra that we look at and we go, oh, that looks sensible.
Right, yeah.
It looks the same brightness as the ATCA spectrum. Who knew?
I'd forgotten that we're getting CAM as a field. Is that right? The chameleon?
We get I probably included no, we're not. That got cut.
That got cut. Oh, okay.
Sorry, I probably had an old slide in there. I noticed that.
Okay.
That
I got excited because I was like, oh, there's lots of HCO plus
we
absorption
could possibly push to get it back if they do give us more time. But
okay, yeah. Because it just means not an HCO plus conference, but we're getting interested in HCO plus absorption because there seems to be a lot of it in the diffuse size, but you can only do it in an absorption. And there's a lot of these observations towards CAM that I think Mary Von Green and Harvey Litz have done. Yeah, they've shown that it's a good tracer of CO dark gas. So
Yeah.
you probably get OH absorption towards those same sidelines. But I mean, if we're not going to get it, then whatever. But we could probably somewhere in gas cap OH have some sightlines. I don't know where.
You could put in a PI project. There is 10% free science time.
Yeah, there's guest science projects, and they're ongoing. So you could very easily put in something for that.
But not yet, because you won't be able to process your data.
Okay, well, ping me again when the pipeline's ready. Okay.
But Michael, that would actually be a good compact array project with mosaicing. You don't need ASCAP.
That's right. Yeah, that's right. I'm gonna write that down. Thank you, John. It's a great idea.
Yeah, and it's always good to get more projects in for the compact array to show CSIRO that it's
very
the community cares about.
Oversubscribed as of yet?
Not really, no. I don't know what the subscription rate is, but it's not.
Factor of 2, I think that's pretty much where we always were.
Well, that's
will
better.
probably
For
be
a while it was lower.
Yeah, I think it will be worse with Big Cat because more people will come and gaps will be, well, actually, on the other hand, it will probably be more efficient to fill that time. So hard to tell.
Yeah, plus with Big Cat, you can get a bunch of lines together. Because like Joe said, you can't simultaneously observe all 4 lines. So we have to get 1612, 1666 for the main lines together and 1720. Whereas ATCA all at once. Every other telescope, I think.
And actually, having said that, some time ago there were discussions about, well, it was posed as bandwidth extension for ASCAP and things like that, basically implementing new modes, because I think we originally planned to have like more than one zoom.
Don't bring that up again, Max. It still makes me cry.
Yeah, well, I know it might be a bit complicated, but yeah, anyway, so I think there were 2 different kind of changes which were required in software, and one of them will only help gas cap and no one else, because like essentially you will have those OH lines captured. You still can't get H1 and OH together, but you would get just OH lines captured in its own zooms with like Windows, probably smaller data sets as a result, because you don't need to get this, big bandwidth with huge resolution. And the second thing will help like other projects, because like say Wallaby could observe split band, I think split band, that's what it was called, and essentially avoid RFI and so on, and EMU would have wider bandwidth. But it looks like as a fraction of the project which just help gas cap didn't fly, although to me it was reasonably easy compared to like all other changes required. Yeah, of course, like now it will not happen, but in principle, technically it is possible.
Good question. So forgive my lack of familiarity with the ASCAP, but what's the smallest spacing, and are we planning on using any single dish observations to get 0 spacing?
22 meters is the shortest spacing. There's splash. We could always try combining. That's always been at the back of my mind, but I'm not even sure you want to. Like, I actually rather like, for me, and it's not going to add anything to the mazes, and for the absorption measurements, there's a lot of clarity that comes from resolving out all the complicated extended junk. But definitely we should try. Okay, it'd be a good data set to have. And we've got parks, and it overlaps nicely, and there's enough overlap in the spatial scales there. It could be done.
Yeah, could I say we do that with the H1?
Yeah.
And it has taken a while to work out, but it's working quite well now.
We'd need to do it with the continuum in, I guess. We'd have to think about it. Yeah, we'd have to think about it. But there are, I mean, the splash single dish continuum was calibrated as good as I could get it, and so I think it's decent within a Kelvin or so in the big beam.
So being synchrotron, is it is it all linearly polarized?
Huh. That's a great question, and I don't know the answer. I just looked at Stokes' eye, so.
Right.
John's shaking his head, though.
Yeah, the linear polarization of the galactic synchrotron is only a few percent in most places. And it's not because it's not polarized when it's emitted. It's just that over the propagation, it gets all tangled up.
Right.
I mean, there's some polarization, but not a lot.
And I think we don't capture linear polarization for gas cap. It's only Stokes V and I.
Yeah.
That's an important question, actually. We'd always thought that we weren't capturing any of the Stokes parameters except Stokes I with the H1 gas cap. But then we found out that actually they were recording all 4 Stokes parameters. And that was useful because it meant we could throw away the others and have more disk space to store our data. But actually, Stokes V is terribly important for both lines.
Do you have any more questions or discussion points? Well, I might take this opportunity then to advertise again this list of surveys that I've got. Let me show you guys how it's developing.
Doesn't have my surveys in it yet, sorry.
No, it sure does. I put them in for you.
You don't even need to do any work. Thanks, Lisa.
Well, I feel confident putting your name down. Yeah, I feel it would be too much for me to put your email address. So I've
you can put my email address.
Any of them that I've been filling out on behalf of other people, because I haven't put people's email address because that might be a little bit too personal. But I wanted to also encourage any of you to, if you know of somebody who has, it doesn't have to be a grand scale survey, just a good chunk of data that you'd be willing to share. It doesn't have to have a name, although we really like our acronyms. Yeah, if you've got anything that you'd like to share, please add it to that list, because we're trying to develop a nice cohesive community here where we can share and get on each other's papers. Also, I've got 3 lists. I've got for codes as well, which is slowly getting, well, it has 3 things on it. Malcolm, I got to put yours on there too.
Anita, can you run Molex, or are you not putting yourself down there?
Molex has changed underneath my Python wrapper, so it no longer works. And I'm on my 3rd new laptop since being able to successfully run it. So I don't think that all the files are in the right spot for my old version of it. So no, I'm not putting my
Okay, fair enough.
I love despotic. That's an amazing acronym.
Isn't that a great name?
Oh, that's commendable.
We should have some kind of a prize for the best acronyms. Also, we've got a list of telescopes. So this, okay. Again, you don't have to be an expert. You don't have to have built the thing brick by brick. Just if you've used it enough that you'd be willing and able to help somebody else out. Or if you know the right people. I think I've got my name here for the ATCO. I'm like, yeah, but I'll help you find somebody who knows more than I do. And also, if a telescope has already been listed here, but you're also willing to help, please feel free to add yourself to that, because yeah, the more people, the better. Yeah, so it's the end of my hijacking and advertising. Do we have any more questions for Joe?
Oh, and those links are on the website, is that right?
Yes, they are. So on the main page of the website, if you scroll down a little bit, the same place where there's like the links to the program and Slack and Zoom, it's all there.
Yeah, and I'll just say that the sessions are recorded. They're in a YouTube playlist. I'm uploading them in my free time, so if you don't see one yet, it'll come up soon.
Yeah, and I'm putting them all in the program page. So the name for every session will have a link to the YouTube video, and then I'm also putting people's slides links in the titles of the talks. So anyone who's given any kind of a talk so far has probably already heard my nice, friendly, increasingly annoying emails asking for slides. So
Yeah.
hopefully we'll have all of those up.
We are very cognizant that the Slack messages delete themselves after, I don't know, 90 days or something. So we're trying to itemize everything and get them saved somewhere for future reference. So that's this initiative.
Yeah. All right. So also the next two sessions that we have today, the last two sessions that we have today, we were setting aside for, people to have breakout rooms to do anything, but it's been absolute crickets on my end. I haven't heard anyone ask. So we have put two things in. So the Thai National Radio Telescope is going to have the first time slot to talk about, if anyone has any ideas or proposals or wants to put their hand up to be involved in the commissioning of that new instrument and getting some science getting done on it. That'll be the first session. And then the second, I shouldn't call it the second because it's the third. Actually, fourth, if we had early morning, it's too complicated with these time zones. Anyway, the next session after that will be about, trying to have a plan to go forward of how to use all these codes and how to make them more user-friendly and approachable and accessible for the average researcher. So if you're interested in joining those, please do. Otherwise, let's say thank you again to Joe for sharing GASCAP and Splash with us. And again, thank you to everyone who came and participated or just were here to listen. Thank you very much.
Maybe we should thank Anita and Michael and Heap, who I know, and anyone else who was involved in setting this up that I might not be aware of, for doing such a great job of bringing, I think it was a really effective online conference, actually. I don't often feel that they're quite as useful as this, so thank you. It was done really well.
Thank you. And actually on that note, I was planning on putting together probably just a slide show, because that's how my brain operates these days, of all the things that we had to do to organize the workshop, with the wink wink nudge nudge intention that somebody else can organize this. Maybe next year we can have another one, because it was pretty successful. Jay, you got your hand up.
Yeah, I just want to say thanks again to all of the SOCs and everybody to organizing, and thanks for giving me a chance to talk. But also, more importantly, isn't it? It's your birthday tomorrow, so happy birthday.
Yes, yeah. Yes, it is.
Yes, happy birthday, Anita.
Thank you.
And I will say, Anita did the brunt of the work. Me and Heap were mostly moral support and hosting sessions that she was either asleep for or too tired for. But
you have no idea how much I appreciate that. Thank you, Michael. I have gotten sleep this week. Cool, thanks, guys. All right, so well, that's it. I'll see you guys in the next sessions then. Bye-bye.
Bye, everyone.